Hi everyone and welcome back to physics. This is Mrs. Hutchinson and today we're going to continue our motion packet and we're going to talk about our guided practice dealing with our 5 equations of motion. What I'm going to do today is I'm going to refresh your memory as to what those 5 equations are. So if you don't have your reference tables out, please make sure that you have them out and flip to the mechanics section just so you can become more familiar with where they are located. We're going to go over all 7 questions, and we're also going to go over the guided practice free fall questions, and then you will work on your independent practice ones. So how this is going to work is just like all of our other videos. I will show you the first question, then you're going to pause the video and try each question as you go. So just a little refresher. Our mechanics section shows us where all of our 5 equations are located. The easier ones are at the top, the ones that we first discussed, our average velocity equation, our acceleration equation, but then we also rearrange our acceleration equation as this particular equation right here, solving for our final velocity. And then we have 2 more equations, one that deals with displacement or distance, and solves for displacement or distance, another one that solves for our final velocity. So, just a little refresher as to what our 5 equations are. Now let's get right into our guided practice here. So again, the difficulty of this is being able to pull the information out of the question itself and figuring out what's given, what are we trying to solve for, and what equation or equations we are going to have to use. So it says a car moving on a straight road increases its speed at a uniform rate from 10 meters per second to 20 meters per second in 5 seconds. Part A wants us to solve for the acceleration. What is its acceleration? And part B says how far did it go during the 5 seconds? So this is actually a 2-part question. This happens quite a bit. So let's first write down our givens. What do we know? Well, if we said that a car is increasing its speed from 10 meters per second to 20 meters per second, that means that we know the initial velocity is 10 meters per second, and we know the final velocity is 20 meters per second. We also know the time is 5 seconds. So those are all of our givens. We know all of that information. Next question is, well, what are we trying to solve for? What's our wanted? We actually have 2 wanteds here. We've got part A and we've got part B. So our acceleration is what we want to solve for part A. And again, you don't have to solve in the particular order in which I ask the questions, meaning you don't have to solve for acceleration first. If you want to solve for displacement first, go right ahead. As long as you obtain the answers, doesn't matter to me how you got there. There are multiple ways to do this, and you're going to learn that. You may have done this in a different way than a way that I'm going to do it. So part B says how far did it go during the 5 seconds, so that would be our displacement. So that's what we're going to solve for here. So we've got our equations. For part A, so we're given our initial velocity, final velocity, time, and we're trying to solve for acceleration. So you can use one of 2 equations. You can use this equation, or you could use the other way that equation is given to us, like that. You'll notice we use that equation because it's got all the variables that are given to us and it's giving us the variable that we want to solve for. For part B, well, you can use multiple different equations if you want to. You can use this equation here, equals VI squared plus 2AD. Or you could use my favorite equation, plus 1/2 AT squared. You can use either one. And many of you might be thinking, okay, well, I don't have acceleration. No, you're right. We don't have acceleration. It's not what was given to us. However, for part A, that is in fact what we're solving for. So we will have it by the time we use part B, or by the time we solve for part B. So just be aware of that. Next, we've got our substitution. So don't forget to substitute with units. I am going to use the first equation here. Whoa, I don't know why I keep doing that. So let's plug in what we are given. 20 meters per second equals 10 meters per second plus A times our time of 5 seconds. Solving for A, hopefully by now you know how to solve for A. And you would get 2 meters per second squared. Okay. So that's part A. I lumped our answer into my substitution section. I apologize for that. I should actually rewrite our answer here. Okay, just so you know. Okay. Next part though, part B, substitution. In fact, I'm actually going to write it up higher. I'm going to write it up here. So part B, substitution. I'm going to use my favorite equation. My displacement equals VI t plus 1/2 AT squared. The reason why I'm going to use that is because it's already solved for in the equation. So you don't have to do any rearranging. You just simply have to plug in the numbers and go from there. So let's go ahead and do this. We got our displacement equals 10 meters per second times our 5 seconds plus 1/2 times 2 meters per second squared times our 5 seconds. Don't forget to put the little square up there. When we solve for this, our answer for our displacement is 75 meters. That's for part B. So a couple of things that I want to note. You could, if you wanted to, solve for each section individually, meaning you could give your given, your wanted, your equation just for part A, and then substitute only part A and give me your answer for part A, and then show a separate calculation for your equation for part B that you're going to use and your substitution for part B. Now, I am not expecting you to be able to pull out which equation you're going to use for the second part just yet. That might take a little bit of time, only because you're dealing with two variables that are unknown in these equations. For example, you didn't know your acceleration for part B until you solve for it for part A. So it might be a little easier to solve for it and then recognize, okay, now our acceleration is a given because I have an answer to it. Just some things to think about. So what I want you to do now is pause the video and try question number 2. So here's how you do question number 2. Hopefully you paused the video, tried it on your own, make sure that you wrote everything in your given, your wanted, your equation, substitution, and your answer. Please make sure that you substitute with units. I know I'm like a broken record here, but I'm telling you, you've got to substitute with units. So a ball initially at rest rolls down a hill with an acceleration of 3.3 meters per second squared. If it accelerates for 7.5 seconds, how far will it move? And how far will it have moved if it had started at 4 meters per second rather than from rest? So we actually have two completely separate questions here. So I'm going to show you how to do part A and part B. Let's go ahead and do this. Okay. So our givens for this particular section, VI, because it says it's starting from rest, 0 meters per second. The acceleration, 3.3 meters per second squared. And our time, 7.5 seconds. So we're doing part A first. Our wanted is how far will it move? So our displacement. Our equation that we're going to use for this, the equation that deals with all of these, so displacement, initial velocity, acceleration, and time is my favorite one. D equals VIT plus 1/2 AT squared. Let's plug all of our information into our substitution. So D is equal to 0 meters per second times 7.5 seconds plus 1/2 times 3.3 meters per second squared times 7.5 seconds squared. And our answer should be pretty easy since this side goes to 0. Our answer for this part is 92.8 meters. Not too shabby for part A. Okay, so now for part B, we have to do something a little different. How far would it have moved if it had started at 4 meters per second rather than from rest? So this was how you would do part A. We're now going to start part B. We've got a couple of things that we have to change. Okay. So let's go over how we would do this. Our given, so VI, instead of being 0 now, is 4.0 meters per second. Everything else is still the same, and in fact we're still going to use the same equation because we're still given the same information, just now instead of from rest we're starting from an actual velocity of 4.0. So now we're just going to take our information and substitute it all in. So D equals 4.0 meters per second times our 7.5, oh that's silly, times our 7.5 seconds plus 1/2 times our 3.3 meters per second squared times our 7.5 seconds squared. We plug that all into our calculumicator, we solve for it, and we get our answer of 122.8 meters for part B. Now, does that make sense? Heck yeah, it does. It makes sense that it would move a lot farther because, well, now it's starting from an actual velocity as opposed to 0. So yes, it makes sense that that would be our distance. So now I want you to pause the video and try question number 3. And here's how you do question number 3. Penny dropped from the roof of a building, accelerates at a rate of 9.8 meters per second squared. It takes 6.3 seconds to strike the ground. How high is the roof? So let's go over what is given to us. So we say that our acceleration is 9.8 meters per second squared. And we know our time is 6.3 seconds. So, things I want you to think about. If you are dropping something off of a roof, what's its initial velocity? It's not too bad. Our initial velocity, if we're just dropping something, just simply holding it and then we just open our hand and drop it, our initial velocity is 0. So they gave you that information, but they didn't give you that information. It's there, but it's not there. So you need to be aware of the term dropped. Our wanted, how high is the roof? That's a fancy schmancy way of saying what's our vertical distance or a vertical displacement. Our equation, yes, you'll see this one a lot. It is my favorite one. D equals VIT plus 1/2 AT squared. And let's substitute everything in. So we've got our initial velocity of 0. We've got our time of 6.3 seconds. We've got 1/2 times our acceleration due to gravity, 9.8 meters per second squared, and our time of 6.3 seconds squared. You'll notice that when you have 0 for your initial velocity, it's always going to go to 0, which means sometimes you don't even need to actually put it into your substitution because it is going to 0. I always put it in just to be on the safe side. And we solve for our final answer. Don't forget this little guy here. If you got this wrong, this is probably why. Your displacement or distance is 194 meters. What I want you to do now is pause the video and try question 4. If you are having trouble with these, make sure that you pause the video and you ask me questions as you go. So pause it, try question 4. So let's do question 4. Hopefully you paused it. A stone dropped from a cliff hits the ground. 3 seconds later, remember we said dropped is a big word. If the stone is accelerating at 9.8 meters per second squared, find the speed at which the stone hits the ground and the distance it fell. So a couple of things we want to solve for here. You can do this as 2 separate questions. So I'll show you what it looks like to do that. So given a stone dropped, so that means our initial velocity is 0 meters per second. We know our time is 3 seconds. We know that our acceleration is 9.8 meters per second squared. Our wanted, so we're just doing part A. Our wanted, the speed with which the stone hits the ground. That means that we're talking about our final velocity here. So this is just part A. Our equation that we're going to use deals with all of these. So pretty simple. I'm going to use the one that solves for the variable that we want to solve for. I'm going to use that one. Of course, you can use this equation as well. It's the same equation, just rearranged. But I'm going to use this one, since it's already solved for me. Let's do our substitution. Okay, so we've got VF equals VI is 0 meters per second plus 9.8 meters per second squared times our time of 3 seconds. So our answer for part A is 29.4. So VF equals 29.4 meters per second. Not so bad. So now that we solve for VF, that actually becomes a given for part B. 29.4 meters per second. So now, for part B, let's solve for what they're asking. They're asking us to solve for the distance that the stone fell. Okay, so we want to know our distance. Can't forget to erase that so I don't confuse you. Part B. So, our equation, which equation are we going to use? Doesn't matter to me. We're given quite a bit of information. You can use my favorite one, D equals VIT plus 1/2 AT squared, or you can use VF squared equals VI squared plus 2AD. Now, I'm going to state I want to solve for displacement or distance, so why not use the equation that's already solved for it, number one. The other reason is, what if, hypothetically, you got our final velocity wrong? Well, now you're going to be plugging in a wrong number into an equation if you use this second equation here. So what I try and stick to is using as much of the given information as we possibly can. If that's not possible, then obviously you have to use an appropriate equation. But in this particular instance, it is possible to use an equation that deals with just the given information. So that's the one I'm going to use. So let's substitute everything in. So we've got our distance. VI is 0 meters per second. Our time is 3 seconds. Plus 1/2 times 9.8 meters per second squared times 3 seconds squared. Our final answer when we solve for this, for our distance, is 44.1 meters. So hopefully that's what you got. If it's not what you got, make sure you pause the video, rewind it, and see what you may have done wrong. Now I want you to, if you got this right, I want you to pause the video, try question number 5. Hopefully you paused the video, tried question number 5. A car traveling at 21 meters per second is uniformly slowed down at a rate of 0.4 meters per second squared. What is the distance it will travel during a 5-second interval? Okay, so let's go through what was given. So we've got the car is traveling at 21 meters per second. So that's its initial velocity, 21 meters per second. It's uniformly slowed down at a rate of 0.4 meters per second squared. So even if you don't know what that necessarily is, look at the units. The units are meters per second squared. So that means that they're telling you that that's our acceleration. It's actually a deceleration. So be careful. It's negative 0.400 meters per second squared. It's because it is being slowed down. Our time is 5 seconds. So the question is, what are we solving for? What is the distance it will travel? So our wanted is our distance. So what equation are we going to use? Yep, it's my favorite. I know. D equals VIT plus 1/2 AT squared. Let's substitute everything in. So we get D is equal to 21 meters per second times our time of 5 seconds plus 1/2 times our deceleration of negative 0.4 meters per second squared times our time of 5 seconds squared. Plugging that all in. Don't forget about this negative value here. So you actually wind up with d, our distance or displacement equals 105 minus 5. Okay. So our final answer, our distance is 100 meters. Okay, not too bad. If you didn't get that right, it's probably because you forgot the negative for our acceleration, because it's actually a deceleration. We know that because it's stating that it was slowed down. So just things to take into account. If you got that right, I want you to pause the video and try question number 6. So here's how you do question number 6. Hopefully you pause the video. A bullet leaves the barrel of a gun 0.5 meters long with a muzzle velocity of, holy cannoli, 500 meters per second. Assuming that the bullet was uniformly accelerated, find the acceleration traveling through the barrel and the length of time it was in the barrel of the gun. So there's a lot that we actually have to solve for here. Figuring out our acceleration, and we're figuring out time. Time is something that we haven't solved for before. So let's write down all of our givens. So we know the distance, 0.5 meters. Now, things I want you to think about. We know our initial velocity and our final velocity. So thinking about if a bullet is in a gun, and we're just talking about the velocity of the bullet, if it's just loaded, and that bullet isn't moving in the gun, what is its initial velocity? Well, it's 0. I know I didn't tell you that, but that is, if you think about it, think about how fast that bullet is moving before it is shot. It's not moving relative to the gun, so it's 0 meters per second. After that bullet has been fired, it moves and it leaves that muzzle with a velocity of 500 meters per second. So that's how we know both velocities. Things you need to take into account. I know it's not necessarily given, but it is given. Our wanted, so we're going to do part A first, is our acceleration. So this is part A. The equation that we're going to use for this deals with all of it. So we've got our final velocity, our initial velocity, our displacement, and our acceleration. So we're going to use our equation of VF squared equals VI squared plus 2AD. Reason why we're using that one is because, well, all of our information goes in that particular equation. So let's plug in our information. We've got 500 meters per second, so don't forget to square that, equals 0 meters per second squared plus 2 times our acceleration, and our distance is 0.5 meters. So plugging that in, we get our final answer of, holy cannoli, that's huge, 250,000 meters per second squared. In other words, you're not going to dodge said bullet. Okay, so don't get in front of it. There's our acceleration. So that information can now become part of our given. So 250,000 meters per second squared. So that now becomes part of our given. Let's work on part B. So our wanted for part B is our time. our equation, what equation are we going to use? You can use pretty much any equation that deals with time. So you can use d equals VIT plus 1/2 AT squared, or you can use VF equals VI plus AT, or you can use this equation here. Okay, the only one that you cannot use is our velocity equation, and here's why: because this is our average velocity. Unless you solve for our average velocity, you cannot just simply plug in our final velocity here. Okay, so you cannot use this unless you solve for our average velocity. So the one that I'm going to use, let's just choose the one in the middle since we haven't used that all that much. So let's go ahead and use that one. We're going to plug in all of our information. So we've got our 500 meters per second equals 0 meters per second plus 250,000 meters per second squared times our time. Solving for our time, you get this very, very, very small amount of time, 0.002 seconds. So it doesn't take a very long time for that bullet to leave the gun. Hopefully you got that right. If you didn't get that right, it might be because you used the wrong equation. So go ahead and pause the video or rewind it to see what you may have done wrong. If you got that right, what I want you to do now is pause the video and try question number 7. So here's how you do question number 7. Pretty simple. A car moving at 16 meters per second is brought to a stop in 8 seconds by applying the brake. Assuming uniform negative acceleration, find the acceleration rate and the distance it traveled after the brake was applied. So let's go through this. Our givens, here we go. We're just going to do it all at once. Our givens, VI equals 16 meters per second. Our time is 8 seconds. And it says it's brought to a stop. So that means that our final velocity is 0 meters per second. Our wanted in this instance, we want to find our acceleration for part A. For part B, we want to find our distance. So our equations that should be used for this part would be for part A, VF equals VI plus AT, and for part B, D equals VIT plus 1/2 AT squared. Again, you can use other equations to help you with this. These are just the two that I chose. Your answers will probably still be the same as long as you plug things in appropriately. So part A, let's plug everything in. So we've got 0 meters per second equals 16 meters per second plus A times 8 seconds. So solving for A, we have -2 meters per second squared. So that's part A. Let's substitute in for part B over here. So we've got our D equals VI, which is 16 meters per second, times our time of 8 seconds, plus 1/2 times our -2 meters per second squared, times our time of 8 seconds squared. So we plug that all in and we solve, and our answer is 64 meters. So this is for part B. and this would be for part A. Hopefully that's what you got. If you didn't get that, make sure that you ask me about it. Now what I want you to do is pause the video and try the front half of the guided practice for free fall acceleration. All I'm going to do is simply give you the answers for those. Okay? If you have questions on those, you can ask me in class. So here are your answers for the guided practice for free fall. I want you to pause the video, read through them, make sure that it makes sense. I'm not going to go over it because it's not too bad. It's simply just a lot of math. You're always starting from rest. Lots of things that you can do. So if you have questions on this, just ask me. Check your answers and see where to go from here. Now I want you to pause the video and try the last page, and I'm going to simply give you the answers for that one. So here are the answers for the second half of this particular worksheet. You just wanted to take each individual section at a time and follow the instructions that are given to you up here. I just showed you one example of what it would be like to solve for the particular time in question. Also part 3, it doesn't specify an initial velocity, so choose your own and compare the tables accordingly. That's up to you. You can do that if you want to. If you have questions on these, you can ask me as you go. Now what I want you to do is the independent practice for the equations of motion. Give me your given, your wanted, your equation, substitution, and your final answer. So do that, and we will go over these for next class. And I'll see you in our next video.